This is a machine to simulate a roadside explosion beneath a military vehicle. The Army's research laboratory wanted a device that's very repeatable to reproduce the energies that a soldier may see from an IED explosion, roadside explosion. It's not intuitive when an explosion goes on in a vehicle, that the first thing that happens is actually the floor crowns, and which means it moves. And if any quick motion to a floor would cause the feet to be propelled all the way up to 15 meters per second.
Wow.
It takes time for the energy to build under a vehicle to lift it. The vehicle does lift, but after the floor crowns, it's usually 5 to 10 milliseconds later. And then the vehicle goes airborne, travels, and in this machine, it comes down directly on it simulates an event of hitting its suspension, which is quite soft relative to the other events. The floor motion can actually cause up to exceeding 700-800 Gs of acceleration to the feet over 2 to 3 milliseconds, maybe a little bit longer, maybe 4. But the energy to lift the vehicle usually takes much longer, anywhere from an event of 5 to 15 milliseconds into the area of 100 to almost 200 Gs. And the last event is much softer because it's coming down on the suspension of the vehicle, the springs, and whatever suspends the vehicle. And that event is usually in the area of 20 to 40 milliseconds, maybe up to the peak accelerations of 50 Gs. And all those events had to be simulated on this machine and in real time, which was the challenge. Well, this is the what we call the VITS machine. It is a 27-foot tall machine, and it can be thought of as in 3 different subsets. The lowest third of the machine is primarily the power and the propulsion system. The mid third of the machine is the impact mass, the control systems, the mechanical levers, and the timing zone. And the upper third would be the table platform and the table travel zone.
So this is the bottom section that we're looking at now, and it's the cylinder to push up the primary impacting mass.
Mm-hmm. There's 2 of them, 2 cylinders.
Now we're kind of looking at the middle section here.
That's the middle section as well. And that is, again, the mechanisms to produce the triggering, the mechanisms to impulse the table platform are all in this middle third. And all the substructure to support it, as well as the programming materials to control the duration and the amplitude of the event. The last third is the table platform and up.
Which you kind of see at the top of the picture here.
Yes. And that's where the test device would be fastened or fixed to the tabletop, and that table will travel through the upper third to simulate the event.
So the bottom part is the energy to get it going.
Yes.
The middle part is imparting that energy into the table.
Exactly.
And the table is producing
the result of all that energy.
Very cool.
Yeah. We could not bias the result by having a free fall event or an accelerated event and an impact. We had to have the product or the test device stationary prior to the event. It has a much different response to the spine having a stationary product. The spine is actually loaded by the weight of the gear, the weight of the human body itself. In a free fall condition, the test dummy would relax into an incorrect position. So the condition was it had to be in the proper position, loaded properly before the impact. Yes, it's much easier to produce a test system that you gain your energy just by lifting and using gravity. that was not an option here. This machine was 27 feet tall.
27 feet tall. So this floor that you're looking at here is
It's roughly
15 feet in the air?
It's roughly a little less, about 13, 14 feet in the air.
But that gives them basically floor level access to the machine.
Floor level access, yes. And so the bottom third is rarely even seen by the operators, of the test operators. Rarely seen. But all the hardware for controlling the impulse levels, the triggering mechanisms, all the power, and all the control systems are beneath the floor level here. Yes.
So it looks like they can put a simulation of the crew compartment on top of this machine.
Yes, this is a quarter section of a vehicle with a test dummy seated in the operator's position, and they are testing it, not only the seat systems and the seat restraints independently, but they are also doing it within their actual surroundings, so that they can see how the seat restraints behave in the real world, in the real environment that are being applied to. The peak velocity on the feet impulse was 15 meters per second. The peak velocity change for the rigid body or the floor motion or the vehicle lifting, if you will, is 7 meters per second. And the slam down also had to be 7 meters per second. If it raises up roughly 9-10 feet in the air, it's going to land with the same amount of energy when it hits. The timing of these events had to be very well controlled into the millisecond zone between the floor motion and the rigid body of the lift. And then the vehicle would lift and then return. And this whole test was over in approximately 1 second.